everybody to the, what is it called, seminars in oncology. I'm Rafael Rizar, I'm the chair of the Department of Data Science, and I'm here to present Bill Lauder. Bill obtained his PhD in biophysics here from Harvard Medical School. Then he went and worked in industry for a while. He was the CTO and co-founder of Deep Health, which got acquired by RadNet, and this was a company that developed imaging AI for breast cancer. He's going to talk a little bit about that. Great. Then we were lucky enough to recruit him away from industry, in the first time in our history, to come to academia, to come work in our department. And he's now an assistant professor in our department and in the School of Medicine. And I'll let you take it away.
Awesome.
Thank you.
Thanks, Rafa. Yeah, so I'll preface by saying I feel like I'm the lucky one. I don't know, or maybe it's mutual luck. I guess this is how things work. But yeah, it's great to speak to you all today. So I thought I'd start by giving a quick context of my background. I think Rafa just covered this, but to set kind of the stage for some of the things I'll be talking about, as Rafa mentioned, so I did my PhD here, and then towards the end of my PhD, I co-founded a company working in medical AI and specifically applications of mammography. And then fast forward, I've been at Dana-Farber for a little over a year now as an assistant professor. And generally today I'll be talking about AI applications in medical imaging. And I wanted to start off by kind of level setting because I feel like there's a lot of hype in AI these days. And it's important to remember, you know, ultimately when we talk about these things, it essentially boils down to something, a diagram like this. We have some type of deep neural network. It might be really big. It might be a large language model. But ultimately, it's a function that takes in some input X, and it's going to make some prediction or output Y. So in the context of mammography, which I've worked on quite a bit, this might look like taking an image of a mammogram and predicting whether breast cancer is present. We can also think of maybe predicting more complex patient outcomes, say maybe trying to directly predict overall survival of a patient given a histopathology slide. And then increasingly, there's more complex approaches of maybe we want multimodal models that can handle not only images, but text, and maybe make multiple predictions at once. But at the end of the day, I want to remind us that, you know, all this is just, it's the algorithm development. It's just one step in the full pipeline of clinical integration. And the way I kind of like to think about AI is more from a top-down perspective of, you know, what is the end clinical goal or even biological goal? And how do we actually want AI to be used in clinical practice? And then use this knowledge to essentially inform how we do each steps along the way towards clinical integration. And so it's this approach of less of I have my AI hammer and I'm looking for nails to hit, but more of a kind of, you know, what is the goal? And if AI can help, let's do that. So, you know, as a quick kind of initial illustration of the steps along this pipeline and the different considerations, I thought I'd start with my experience in mammography. And so in general, when I'm looking at research questions, there's three things I tend to look at. One, is it a clinically important question? Two, is there theoretically at least data available that we can use to train these AI algorithms? And third, even if we can develop a super cool algorithm, is there actual potential to get this into clinical practice or at least answer kind of basic biological questions? And so when I started working on mammography, it was clear it kind of checked all these boxes. And of course, with all these AI algorithms, you typically need to collect a lot of data to train them. I'll skim through some of the details here, but we essentially collected data from a number of different clinical sites. The other point that I want to make when it comes to kind of the algorithm development, as much as we can boil it down to this simple diagram, of course, it's, you know, it's really a devil is in the details problem, where oftentimes in medical imaging and medical in general, you really do have to adapt to the problem at hand. And here's again an opportunity to really think about this clinical integration aspect of what ultimately do we want the algorithms to output, and even types of data we want it to work for. So again, I'll skim over some of the algorithmic details I'm happy to talk about later. But essentially, we developed an approach that works for both 2D and 3D mammography and is able to handle different types of data and make predictions in kind of an interpretable fashion for radiologists. And so once we have an algorithm, again, there's many different ways to get there. If we want to integrate this into practice, we need to build some type of interface that clinicians can work with. And again, this is where we can think about how do we want this thing actually be used. In our case, one of the products we developed is called SageDX, and it's essentially minimal by design. The idea is a radiologist is reading a mammogram on their normal workstation, and they can simply click a button and the outputs of our AI pops up. And this consists of bounding boxes to highlight suspicious lesions, as well as what we call suspicion levels that essentially give a categorical score of a degree of suspicion. And of course, we want to show these things ideally work before we go and clinically deploy them. So one aspect that I think there's a lot of progress and more work to be done is how do we evaluate these AI algorithms. And a lot of times, these AI algorithms are often kind of evaluated in a box. It's kind of, we test the performance of the AI itself, but ultimately we need to think about where these fit into clinical care. So in the case of our product, our goal was to not, say, autonomously interpret these exams, but to aid radiologists as they interpret the exams. And so in particular, we did what's called a reader study, where the goal is to assess how radiologists' performance changes when they actually use the AI. So you get a set of radiologists, a set of mammograms, and the radiologists essentially read the mammograms twice, once without the AI and once with the AI in kind of a fully cross fashion, and you want to measure this change in performance. So we did one of these studies, and we saw that indeed radiology performance significantly improves along a number of different metrics when they used our AI software. And we saw this improvement essentially across all the radiologists that participated in our study. So this was at least some initial evidence that we felt we were on the right track, and the performance we saw was kind of bigger increases than had previously been reported. So we took all this data and a few hundred pages of product documentation and FDA documentation and took this to the FDA, and ultimately had a few FDA clearances at this point. So we have a couple products that got FDA cleared. And finally, coming to the clinical integration perspective, as Rafa mentioned, our company was acquired by this larger company called RadNet, who's essentially the biggest outpatient imaging provider in the US. And so I worked at RadNet for a couple years to clinically integrate our products, where they're currently processing a little over 1 million mammograms a year. And so, of course, this whole process is not linear, and it, of course, doesn't end at clinical integration. We really need to monitor these things over time in practice. So we're still early days, I would say, in this evaluation. But our initial real-world evidence does point to clinical utility. So if we simply measure the change in performance pre versus post-deployment of our AI software, we do indeed see a significant increase in the cancer detection rate. There's also a slight increase in recall rate, pointing to this need for kind of monitoring how things evolve over time. But long story short, I think we're a long way to go to show that these things work prospectively across different applications in clinical care, but initial evidence is positive, and there's also been other studies pointing these directions as well. Okay, so I kind of just breezed through the application in mammography and the steps along the path. But of course, mammography is just one application. And as much as there's talk about AI and even hype, we felt it's useful to gain a better grasp of what else is actually out there in the field and what is actually FDA cleared and available for clinical use. So in a recent study, myself and led by Stephanie McNamara, who's a MD PhD student here at Harvard, we essentially went through all the FDA's databases and created a curated database of FDA-cleared products in medical imaging AI. And just to give a little bit more details of this, so if you get an FDA clearance, the public-facing document is called a summary statement, and it essentially summarizes what the product does, its outputs, and how it's intended to be used. So we manually went through several hundred of these documents, and we found a number of different applications, but they all essentially fell into a handful of different categories in the way they're supposed to be used. So there's this term that's used, CAD, which refers to computer-aided detection. And essentially, there's different variations of these different CAD products out on the market. So the one I talked about is referred to as a CAD-E, CAD-X product. So the idea is it detects lesions and then also gives some type of score to help make a diagnosis. So if we unpack it a little bit, the E in CAD-E stands for detection. The X stands for diagnosis, where the score is supposed to help actually make the diagnosis. So it's a bit of word soup, admittedly, but these kind of detailed considerations are important when we think about how are these actually supposed to be used. So in addition to these kind of combined CAD-E, CAD-X products, there's also examples where it's only the detection part, so CAD-E, or only the X part, the diagnosis part. So all of these products are essentially designed to aid radiologists or clinicians more generally as they're interpreting exams. There's another use that's becoming increasingly popular, which is known as CAD-T. And so the T here stands for triage. And the goal with the triage product is to flag cases before they're even reviewed by the clinician, to identify these suspicious exams so they can maybe be reviewed sooner than they would otherwise. So a canonical case here might be in an emergency setting where, say, you have a patient that just got a head CT and you want to quickly determine, is there a high likelihood that the patient has maybe a stroke? And if so, can we get the clinician to interpret this exam sooner? So this is before the clinician interprets the exam. There's also a variation of CAD that's emerged that actually autonomously interprets the exam. So there's one specific application where this is the case on the market, where the AI is essentially the sole and only reader of the images. And I'll get to that specific application in a minute. Okay, again, so there's a ton of different applications right now in terms of diseases, but they all fall under these kind of 5 different CAD types. And if we go and look at the actual distribution of these in the FDA-cleared products, we see that these triage applications really dominate. So in fact, there's over 100 applications currently cleared, and the CAD-T makes up the majority of them. But there are some representation of each of the other variations. And now if we dig into the actual diseases that are covered, since this is an oncology seminar, if we first kind of focus on cancer applications, indeed for at least the 4 most common cancers, they're represented on this figure. So there's applications currently for breast cancer, lung cancer, colorectal cancer, prostate cancer, and a few other ones where there's maybe 1 or 2 products around. And then, of course, there's many other diseases represented. And if we look kind of even more generally, what type of modalities do these algorithms process? We see that radiology applications dominate, so things like X-ray or CT, even ultrasound. But there are a few applications for, say, colonoscopy. And currently there's one FDA-cleared product that processes pathology whole slide images. Okay, so one of our core goals in creating this database is to really understand, what are the outputs of these devices, and especially how it relates to this notion of explainability. So explainability is a bit of a loaded term these days in AI, but essentially the notion is, how does the AI convey its predictions to a human and kind of explain the rationale of why it's making its predictions? And so when we look through all these products, there's essentially a few different categories that emerge. So one is essentially no explainability. The AI simply makes an image level prediction, but doesn't really give much beyond that. The next level down would be what we're calling localization-based explainability, so maybe pointing to the location of a lesion. And then there are a handful of products to do other things of, say, maybe giving semantic descriptors, describing a lesion, or even quantifying maybe the size of a lesion. And one product that actually essentially retrieves similar looking images from the training data set to the image currently being viewed. So a bunch of different terms, but what I want to point out again is that if we look at the product count that are FDA cleared, we see that the non-explainability is by far the most prevalent again. And this in large part is driven by these triage products. And then when explainability is provided, we see that this localization-based explainability is the most common. And then there's a handful of products of the other explainability types. So as we're thinking about how do these actually integrate, how do we want them to be used, it's not necessarily that no explainability is kind of a deal breaker. And the FDA's rationale for this is in the triage setting, these products are just supposed to flag cases, and then the radiologist or clinician does their normal review as if everything else was kind of the same. They just do it in a prioritized fashion. But of course, when you get to the real world, that's not how things work. People kind of take the products and use them how they might. And so actually, the FDA recently released a letter to healthcare providers informing them of this intended use and really calling out the intended use of these triage products, specifically in the context of large vessel occlusion. So one particular application that's popular for these triage devices. And if you go through this letter, you see they have some recommendations of trying to remind people, hey, these are just supposed to flag things. They're not diagnostic. We had to use them as they're intended. But it does come to this point of, again, really thinking about how we want to use these products and connecting to these notions of explainability. Okay, so quick interim summary. I kind of give an overview of where we currently stand in medical imaging AI. So there's a number of FDA clearances for different applications at this point, where some of these applications are starting to be clinically deployed and progressing into prospective use and even evaluation, for instance, mammography. And generally, there's a high concentration of radiology-based applications, and especially for triage and detection tasks. And then finally, there's often limited explainability of the AI predictions. So as I mentioned at the beginning, as Rafa was saying, he was lucky for us to kind of be together. I feel lucky that I now have kind of the research opportunities to address these questions as we build next generation AI applications. And so my group has been working on kind of a number of these directions. And so next I'll talk about kind of initial efforts in this domain that we're working on. So first, starting with kind of more methods approach of developing more enhanced explainability techniques for AI algorithms. So again, if we formulate our algorithm and say we have algorithm that's going to predict whether breast cancer is present, if you have something like this, it naturally raises questions. Is the algorithm using the same features as a radiologist? Has it potentially discovered new predictive features that might inform kind of biological discovery? Or maybe has it even learned essentially shortcut connections or spurious correlations in the data set that essentially allow it to cheat when it's making its prediction? And as we've seen, the kind of standard approach of explainability essentially answers the question of where behind an AI model's prediction. So essentially pointing to the location of the lesion and giving some sense of localization. But of course, if you were to talk to a clinician and ask, why did you deem this to be suspicious for malignancy? They might say, oh, well, it's a spiculated asymmetric mass, and they might say it changed over time and give some more context of essentially the what and why behind their prediction. And so we'd love to have AI approaches that can also give us this what and why explanation. And this is where I particularly got excited about large language models. Of course, everybody's heard about these things these days from, say, ChatGPT. And perhaps we can use these models to give us more language-based explainability for visual tasks. But for anybody who's played with these things, there's the propensity to essentially hallucinate and make things up. So we need to think about carefully, how are we actually going to do this so the explanations are actually faithful to the concepts they represent. And so we had a couple other requirements we had here, and we pieced this together and came up with an approach. And this approach specifically leverages multimodal models. And I'll say this work was led by a student in my lab, Shobit Agarwal, and he's done great work. So we specifically use this model from OpenAI, known as CLIP. And the whole idea behind CLIP is it essentially represents text and images and learns a joint representation between the two, such that, say, an image of a dog and a caption describing the dog would essentially have a similar representation in this kind of joint representational space. But then if you have a caption, say, describing a cat, it's going to kind of live in a different position in this space. And so we took this model, and our idea was, well, can we train this model to learn a new visual task and use this joint representation to assign language-based descriptors to that visual classification task. And so our first step proceeds of taking a set of images. Maybe we have the breast masses, and we use this image encoder from CLIP to learn a new classifier to classify benign versus malignant lesions. And then for the second step, we essentially take a bunch of words that are kind of general purpose words of how would you describe a visual object. You might use adjectives of large, round, small, these type of things. So we take this dictionary of words and we pass it through this CLIP language encoder. And the crux is that since this language and the images live in the same space, we can think of the words now living in this joint space. And our approach proceeds by trying to estimate the visual classifier as essentially a weighted combination of words. So maybe malignant means 0.5 large minus 0.3 round, and so on and so forth. And the upshot is we get these weights that essentially indicate for each word its alignment with the visual task, at least what the model has learned. And so we had some initial preliminary work with this approach. And we first started with, in the case of mammography, classifying benign versus malignant masses. And we see that when we do this approach and we squint hard enough, we can rank each word in terms of how much it correlates with malignancy versus a benign lesion. And the words that jump out, actually, at least the top scoring words, kind of clinically make sense. I'll say I'm not a clinician, but at least from what I've read and what people have conveyed to me, malignant lesions are more likely to be, say, asymmetric and large. Benign lesions are more likely to be round and symmetric. And in between, it's a little more questionable. There's a little more scattering of different concepts. But it's kind of interesting in that we didn't force the AI model to use these terms, but simply trained it on the data. And the things it learned kind of generally aligned with clinical intuition, suggesting, okay, maybe it's kind of doing something that makes sense. We can do this for, say, a skin lesion task as well. And again, I'm certainly not an expert here, but the top scoring words in each direction, they kind of align with this ABCD rule, which is talked about in dermatology. And so, round and smooth lesions are more likely to be benign, and so on and so forth. Okay, so we developed this method for explainability, and the goal is we want to be able to convey information to humans. But one challenge is, how do we actually even evaluate explainability? I can kind of wave my hands and say, yeah, that kind of makes sense. But we did, to kind of get more functional assessment of this information, we did another reader study. And the idea was, if the terms that come out from this task are actually generally interpretable, then we should be able to give them to a non-expert human, and it should allow them to perform the task above chance levels. So they're not going to be as good as a clinician, but if they understand what the word large means and they can kind of visually pick up these features, then they should be able to maybe do the task above chance levels. And indeed, in a small-scale study, we did see this be the case. So if we first just had the non-experts interpret the images, we saw that they were essentially at chance. Then when we gave the AI-identified terms, again, not huge increase in performance, but a significantly increase, so they're now able to do the task above chance levels. And finally, at the beginning, I mentioned, one motivation for this work is essentially trying to understand, when do AI models cheat, and can we come up with methods to identify this? So I'll give a quick illustration of how we can use our method for that. And so, for instance, in the context of these skin lesions, a lot of times dermatologists might make a marker kind of mark around the skin lesions to indicate kind of suspicion that needs to be followed up. And essentially, in our approach, we can identify this word marker actually aligns with the model's prediction. And it's essentially learned this confounding factor in the data set where if the marker is present, it's going to naturally upclassify the lesion. So it's one of these things where the AI seem to generally use terms that clinically make sense, but there is this propensity for the AI model to cheat if these correlations exist in the data set. Okay, so I just talked about some work we're doing on explainability of AI predictions. Now coming back to this more application-focused question, and as we've shown that a lot of applications have focused on triage and detection in the radiology domain. So in the context of oncology, a lot of these applications fall in essentially screening and cancer detection tasks. So the initial detection of cancer. But of course, there's plenty of opportunities to use AI further down the clinical pathway for the definitive diagnosis and maybe classification of the cancer, and even optimizing, maybe predicting patient prognosis and optimizing treatment. And so certainly there's a lot of great work happening in these tasks, including around the Farber. But generally, these are still farther from clinical adoption than the screening and detection applications. So we've been excited about working in these new domains. And one project we're especially excited about is this project known as ImmunoProfile. So for those who aren't aware, ImmunoProfile is essentially an institution-wide effort performed here at Dana-Farber, and it consists of a multiplex immunofluorescence assay. I'll try to say that again, multiplex immunofluorescence. The upshot is that it produces these pretty images where we can tag different proteins and identify different cell types, for instance, tumor cells and different types of immune cells. And this project has been ongoing certainly before I got here, and it's been a lot of great work for a number of people involved. And my group has been working a lot with Scott Rodig and James Lindsay to analyze this data. And a postdoc in my lab, Cassie Hobel, has done a lot of the analysis I'll now present. So again, this ImmunoProfile cohort was an assay that was run prospectively in kind of a pan-cancer diverse setting here at the Farber. And it resulted in this interesting data set where we have over 20 cancer types represented. There's mixes of different stages, other clinical variables. And so the first thing we thought is, what can we do with this rich, diverse pan-cancer data set? And can we even try to kind of understand and describe the data as a first step? And so here the thought was, people talk about different types of tumors, maybe hot and cold, and different types of characteristics. Can we, in a more data-driven fashion, understand the structure of the tumor immune microenvironment using this cohort as our data set? And so as we think about describing this cohort and the overall kind of maybe distribution of different cell types, often the first place you start is quantifying maybe the counts of different types of cells within each tumor. So you might think of quantifying the density of CD8 positive immune cells within the tumor and quantify this across tumor types and look at different correlations. And that's definitely an interesting route, but there's increasingly interest in looking at not only the composition of the microenvironment, but also the spatial arrangement. So as a first order as a first order approach, we came up with a metric that we're terming the proximity score. And the idea here is whether or not we have a lot of immune cells, can we measure, are those immune cells more proximal or distant from the tumor? I'll spare some of the math, but this kind of illustration of two examples shows the overall concept. Where on the left, we have a tumor where the immune cells have really infiltrated the tumor or are proximal to the tumor cells. On the right, there's essentially the same number of immune cells, but it's clearly a different spatial structure where it's more of a excluded or compartmentalized environment. Okay, so now we have a metric that we can quantify at least first order spatial structure of these tumors. We can also think about the counts of the different immune cells. And so again, coming back to letting the clinical question and biological question dictate our approach, what we did next is actually a simple PCA, principal component analysis. The idea being we have these different markers. We can measure the density of these different immune markers. We can look at TPS, tumor proportion score, positivity score for say, PD-L1. And then we have this proximity score we can also compute for each of the immune cells. And with all these, can we understand just the basic independent sources of variation across the data set?
You have a matrix that has each cell is a row, and then each column in some feature?
Yes, similar, yes. The rows are at a tumor level, essentially. So any given, any given tumor, we can quantify the density of, say, CD8 cells and these proximity scores. So it's at the tumor level. The dimensions, so the cohort has about 2,000 tumors, and we have 9 components, or 9 features we included in the PCA. So next I'm going to show you a bunch of numbers, and I'm going to try to walk through these numbers. But essentially, if we take all the tumors in the data set and quantify these different metrics and pump it through the PCA, what comes out are this notion of these independent sources of variation across the data set. And so if we look at the first component, which explains the highest source of variation, we see that it puts a lot of weight for the density of these immune markers. So kind of regardless of the cell type, whether it's a CD8 positive immune cell or FOXP3 positive immune cell, it kind of conveys this notion of a hot versus cold tumor. So if you're scoring high for this phenotype, it means you have a lot of kind of infiltration, and low means it's more of a cold tumor. So this is somewhat interesting in that we're using an unsupervised approach, but it kind of, again, came out to be clinically and biologically meaningful. If we go down on the list, the second component looks more at this proximity score. So less about whether you have a lot of immune cells present, but how close are they and proximal to the tumor. On the third component, going down the list, it's looking more at this interaction of PD-L1, both at the tumor level and whether PD-L1 positive immune cells have kind of infiltrated the tumor. And then finally, the next two components look at this difference between essentially CD8 positive immune cells and FOXP3 positive immune cells. So for people who are much more experts than me in kind of immunology, this is essentially looking at the difference of the cytotoxic immune cells, which can normally kill cancer cells, versus the T regulatory cells, which are more immunosuppressive. So do we have more of a kind of cytotoxic versus immunosuppressive environment? So again, the precise numbers aren't necessarily that important, but the thing that comes out, again, is that these biologically meaningful concepts that we can use to essentially classify different tumors. And so to illustrate this a little bit more, again, the first component looks at essentially the density of immune cells, kind of this variation between hot and cold tumors. The second component is more on the spatial arrangement of the immune cells and whether they've infiltrated the tumor or have more of a compartmentalized environment. And the next components, again, this third component is looking at this PD-L1 axis, which for people who are familiar is highly important in, say, immune checkpoint inhibitors. And then the next components is looking at this kind of cytotoxic versus immunosuppressive phenotype. Okay, so that was all to kind of show we can use this data in a pan-cancer setting to better come up with a classification and understanding of the structure of the tumor immune microenvironment. Next question we can ask is, okay, great, how does this vary across different tumors? And so for any given tumor, we can essentially classify it for any principal component. Are you kind of high or low in this component? So for instance, on this first row here, I'm showing the distribution of the immune cell density, essentially hot versus cold across tumor types. The point I want to make is that certainly there are some cancer types that tend to be, say, more hot or cold on average. For instance, head and neck cancers tend to be hotter versus, say, renal cell carcinoma, more on the colder side. But for any given tumor, there's both a representation of both, say, hot and cold. So it's never all or none. And we see this across each of the different principal components. And next, we can ask, do these different phenotypes correlate with patient outcomes and just basic patient prognosis, say overall survival? And these features don't necessarily have to. Again, we're using kind of an unsupervised discovery of the structure. But we do see that if we simply correlate the values of these features across tumors with patient outcomes, a number of the features come out to be significant at different tumors, for different tumor types. And so for instance, if we focus on this first column here, this is again looking at more hot versus cold tumors. Not surprisingly, in a number of cancers, it turns out that the hotter tumors, more inflamed tumors, generally have correlate with better patient prognosis. The second component down the list is looking at the spatial metric. And here there's a little more variation, where in some tumor types, it seems that the more infiltrated phenotype correlates better with survival, where in others, it's more this compartmentalized phenotype that seems to be better. This third component is a little bit more consistent across cancer types, where essentially a more PD-L1 expressing tumor tends to be worse correlated with survival. And similarly, we can look at the other components and even look, say, maybe not across cancer types, but across stage. Generally, when we're looking across stage, we again see mostly largely consistencies, but maybe some interesting nuances between, say, early stage versus late stage that we're currently digging into. Okay, so again, we kind of took all this data and we're just trying to make general sense of it. And we do see these kind of unsupervised structures emerge. But it turns out that if we simply just use the density of, say, CD8 positive immune cells, the overall prognostic accuracy of that marker is larger than any of these individual principal components alone. And if we combine the principal components, we do get some boost in prognostic accuracy, but it doesn't give a lot of bang for your buck versus, say, just looking at CD8 density. So we're currently working on, well, can we now use deep learning, bring in our AI hammer, and try to directly optimize for predicting patient prognosis? And so here, again, we started off looking at these kind of hand-tuned metrics of maybe different cell densities and these proximity scores. On the other end of the spectrum, we have the raw images themselves, and we can imagine using image-based deep learning and make predictions directly from the image pixels. But given kind of the size of the cohort and different biological questions we wanted to ask, we pursued a more middle ground approach. And here we're using graph-based neural networks to predict patient prognosis. And how these graph neural networks work is essentially we can take a tumor and represent the neighborhood structure of the tumor as local graphs, where essentially each node in this graph is a cell, and then neighboring cells are connected as edges in the graph. And each different cell is classified by its cell type. So using these different expression markers, we can classify, say, tumor cells versus different types of immune cells. And so with this, we can ask questions, okay, given local neighborhood structure, so both the kind of composition and spatial arrangement, with this information, can we directly predict how well a patient will do? So it looks like a schematic of this. So we form our neighborhood graphs. We pass it through different types of graph neural networks, again, trying to directly predict overall survival. And once we train this, we could then perform essentially a patient-level prediction by making predictions across all the subgraphs and essentially aggregating these predictions to create one single estimation of a patient prognosis. And so this is still definitely early work and work in progress, but it turns out we can actually do this. So if we specifically focus on non-small cell lung cancer, which is the biggest representation in the cohort, and we just directly, through end-to-end deep learning fashion, try to predict how well a patient will do, we see we can indeed predict prognosis better than these density and kind of hand-tuned metrics. So I'm showing one illustration here where we can quantify it in different ways, but say if we're using the concordance index using 5-fold cross-validation, we get a meaningful boost in performance than these density metrics alone. So again, early work, still a lot to be done, but we're trying to merge this kind of unsupervised approach with this kind of direct end-to-end deep learning methods. Okay, and so coming back to kind of where we started and where we're going, so as we're looking forward to future applications of AI in medical imaging, we envision there's an increasingly focused on prognostic and predictive applications. So not only using AI to, say, detect cancer, but can we use it to optimize how cancer is treated? And from the methodological standpoint, there's increasing efforts on these explainability approaches, especially as LLMs emerge. Can we give more intuitive explainability that ultimately help optimize this kind of clinician and AI interface? With that, certainly all this work was real group effort. So I want to thank a lot of folks in my lab, across Dana-Farber and Harvard, folks at DeepHealth and RadNet, as well as external collaborators. And with that, I want to say thank you.
I'll shout just as the mic comes. But
Yeah.
So a question that I have for you, just kind of in terms of the next generation, looking at kind of patient prediction and not just diagnostic software. With your neural networks, one of the main things that you lose is explainability unless you integrate it into other large language models. And so, and with neural networks, one of my first questions is always is it necessary to use a neural network? And have you run these things with just more standard regularization and decision tree based and all the other variations of those? Because with decision trees and boosting, you can get a much more explainable model at the end that might be better, for actual clinicians. And so have you run those models, and do they perform just as good or worse than your neural networks?
Yeah, absolutely. Great question. I think it depends a lot on the application and what the data looks like. So one challenge, specifically when you're looking at medical imaging, is what type of features do you use to make these predictions?
Well, yeah, and I guess you have your 9 features that you ran through your PCA, and it seems like the PCA doesn't work, but you still have 9 features that that would be easy enough to run through simple decision tree and regularization
for sure.
models.
So in that approach, for specifically the multiplex data, it's kind of a little bit more structured, so it's easier to come up with these features that we think are meaningful. And so I kind of skimmed over some of the analysis, but yeah, we have played around with just using these 9 features. Can we predict patient prognosis? And again, we see some boost in performance based on baselines of like just the density of different types of immune cells, but not a ton. And so that really pushed us, well, can we learn more complex features in a deep learning fashion? And that we are seeing this boost in performance. But to your point, it's not necessarily the case that just a boost in performance leads to better clinical care. And so we're actively using these explainability techniques to say, can we identify maybe new spatial biomarkers? And then there's perhaps ways to then actually quantify those biomarkers themselves and use that as kind of the biomarker going forward instead of just the AI's prediction. But yeah, great question.
Thank you.
I can start, Charlie. So the very last part of the talk, very interesting. I was wondering, like, twofold question: how do you control for like stage of disease?
Yeah.
And do you have any independent validations, or how do you plan to have this? Is not trivial to produce these data sets.
Yeah, absolutely. Great question, and something we're actively working through. And so some work we've done, and a lot of folks, collaborators across Dana-Farber, we have developed more kind of standard statistical models that control for stage and use these as covariate factors. And we do see that, for instance, the density, I don't think I have a slide for it, but some of the density markers still do come out as being prognostic, even when we control for stage and these type of things. When for the neural network analysis, we're also considering maybe including stage as input to the network. At the very least, you could do subgroup analysis to see does the prognostic accuracy hold within stage. And then, of course, there's tumor-specific questions of subtypes. So certainly agree, you kind of need to do these in a really detailed fashion. To your point of external validation, there are a few public data sets that we're starting to work with that don't necessarily have the same number of markers and these type of things, but we can at least use it for initial validation. But yeah, absolutely great point of we need to show that these work robustly, or at least within our constrained set of markers they work. So we're actively working on that.
So I'd like to ask, going back to the breast cancer mammogram
Yeah.
example. So was this done starting with a set of mammograms that were proven to be biopsy positive for breast cancer? And then, so it's a training set, a large number that were positive and a large number that were negative, and then applying your neural network to discern features?
Yes, that's exactly it. So we train on biopsy-proven cancers, and then for negative, we require follow-up. So the radiologist said, cancer isn't present, and then we follow up the patient for their next screening exam, confirm that they're negative for breast cancer, and treat those as negatives.
Yeah, and then after you've developed a model, and when you test it and you say, oh, it's better than just the radiologist, then is that using similar sort of metrics that way, that you say, oh, they had a biopsy, they had cancer?
Yeah.
Or the other cohort where you say, no, there's nothing here, then those get 5-year follow-up to prove they really did not have breast cancer lurking at that time?
Yeah, great question. I'm trying to go back to results. So in this particular study, yes, so there are different types of cases included. The kind of confirmed negatives, the radiologist interpreted as negative. We follow up 2 years to confirm negative. Then there are kind of biopsy-proven negative, and maybe the initial radiologist recalled the patient, but then it was biopsy-proven as benign. And then there are the cancers that were biopsy-proven. And for this particular study, the data we used were from sites we had never touched before, and radiologists that were independent. And so we essentially use that data as ground truth to assess performance.
Okay. And then, I'm sorry to monopolize all your time, but then going to the lung cancer example at the end.
Yeah.
So again, was this trained based upon known survival outcomes?
Yes.
To generate your GNN versus your, I don't know what those acronyms stood for anymore.
Yeah.
The two sets.
Yes, exactly. So
So is this a leave one out analysis, then you apply it to the remainder of the data to come up with, to show that it validates?
Yes, a great question. And that one we did five-fold cross-validation.
Okay.
Yeah. But yes, follow-up to get overall survival data and censoring, and then use the five-fold cross-validation there.
Thanks for an amazing talk. So I'm in gastroenterology, and we're essentially building an image and video library for general and advanced endoscopic procedures. And we're having some issues with annotating these huge mountains of data for videos and images. And so I just kind of wanted to get your perspective on how much annotation do you do? Do you annotate everything? Do you annotate 5%, 10%? What's been the approach usually? Thanks.
Yeah, great question. And to your point, there's the raw data itself, but then there's also the annotations that train the data. So it's not as simple as just collecting the data. Of course, we need these annotations. I think it really depends. And of course, there's increasing work using maybe unsupervised or self-supervised methods. And even when we're talking about annotations, there's different levels of annotations. So there's kind of weakly labeled data where maybe you know cancer is present, but you haven't had a clinician annotate the location of the lesion. And then when you annotate the lesion, it's kind of in a strongly supervised fashion. So for instance, in the approach we developed for mammography, I'll spare trying to clicking through all the slides, but we leveraged a little bit of both. So we had some smaller set of annotated examples. And then from that, we see you can kind of initially train a model. And then from that, if you can use the weakly labeled data to essentially fine-tune it. Maybe unpacking that a little bit more, you can imagine for these medical images, if you were simply just straight give it to the AI algorithm and say, cancer is present, it could easily overfit. Where do I look? But if you kind of bootstrap the algorithm and kind of teach it this is what a lesion looks like, then at that point you can kind of fine-tune on this weakly supervised data. But to get to the extent of how much data you actually need, I think it can definitely be domain specific. But one of the interests around these foundational models now is that maybe you don't need as much training data if you can do your pre-training on other data domains. But historically, the rule of thumb is, if you want to recognize dogs and cats, you need 1,000 dogs and 1,000 cats. I think we're pushing down on that, but typically my rule of thumb when I'm talking with collaborators is a couple hundred labeled images at least. Thanks.
So my question is related to the mammography and the using of LLM. So I'm assuming that you were using electronic health records, or you use some other description from the radiologist?
Yeah.
My other question is that have you considered using other parts of the electronic health record for training, and especially when you are training for prediction, would it make sense to use the afterwards the pathology slides or report of the positive breast cancer in connection with the mammography to train for prediction? Thanks.
Yeah, it's a good couple questions in there. Maybe to your first point of what, are we using the radiology reports? For our specific approach, the idea is that we don't actually need the, let me think of how to motivate this. So the idea is we're discovering the language in a more unsupervised way. So we have this pre-trained encoder that kind of knows that has this kind of vision and language in this domain. And then we fit a new classifier that still lives in this domain, and then we can estimate it. But certainly that's kind of a simplistic approach, and we are now actively working on, well, can we use more kind of domain-specific language and maybe even not use a general purpose multimodal model, but one specific for radiology. And to your other point of kind of training down the line, I think, yeah, there's a lot of interesting directions there of efforts essentially from maybe more cheaper or available data. Can we predict more complicated or further downstream data? And so there's approaches of not only saying detecting cancer now, but predicting future cancer risk. You can argue of maybe predicting the subtype of the cancer from the mammogram alone and these type of things. And from my perspective, I think a lot of it comes down to what will actually be clinically useful and at what threshold of performance does it need to be to actually be useful. So if you can predict, say, subtype from the mammogram up to, say, 60% accuracy, is that ever going to prevent you from doing the biopsy? So I think these are the kind of questions we need to think about.
Yeah, I know that you just showed that the accuracy is better if it's only AI and not in combination with the radiologist. But in those settings when a radiologist and AI is working together, is the workload actually less or more on the radiologist?
Another great question. So the goal certainly is to reduce the workload, but that comes into this question of like where does it actually fit in the clinical pipeline? We have seen that when radiologists use our product, they improve both in performance, but also some evidence on efficiency. So especially in the case of mammography, in a screening population, maybe 1 out of every 200 women have breast cancer. And so that means the vast majority of patients thankfully don't. And so especially on that lower range of suspicion, so maybe when the AI says, look, there's really low suspicion, we have seen evidence that radiologists can maybe speed up a little bit or it improves efficiency. And there's other work also shown this as well. So ideally we hit both improve accuracy and improve efficiency.
Sorry, last question. So
Yeah.
you have shown that the non-radiologist is getting better after using AI. Is the radiologist getting better after using these tools, or?
Yeah, another great question. So for this specific study, these were all radiologists and they're expert, board certified, and so on and so forth. And so when they used our AI here, they got better. For this kind of initial explainability work that I was showing, it was more of a pilot study of, and that was just with non-experts because we felt that, like clinicians already know that like larger lesions tend to be more malignant. It wouldn't add new information to them, but we hope to in the future use more sophisticated approaches and then aid radiologists with this as well. But this initial task was kind of initial proof of concept.
Yeah, I was thinking about like using it almost like a training tool also.
Yeah, that's certainly a great idea, for sure. Alrighty.
Hey, Bill.
Yeah.
Really nice talk.
Thanks.
I can call Michelle. You mentioned some of the situations where the model would cheat using kind of spurious correlations and identifying situations like that. I guess I was wondering about what comes next when you run into that kind of thing. Is it really hard to try to, like, do you force the model to not use that particular trend if you identify one, and is it really hard to do so?
Yeah, that's a great question, and I think it's currently unsolved. Because, ideally you'd say, hey, you can't use it, but how do you actually do that? I mean, one, you could try to remove it from the images itself. That is probably never going to work perfectly, and it's going to be able to detect that. So I think how I see it is maybe we can use this as safeguards to, if this confounder is present, let's at least flag it and say, hey, maybe you shouldn't trust the AI here. So that's kind of the initial step. It's like almost a deferral to predict type thing. There are increasing approaches that try to maybe learn a new representation that kind of factors that information out. You can imagine trying to do that, but at the same time, it's like clinicians can also, like, I've heard other folks say, well, like, clinician might kind of cheat there too, a resident, because they know a clinician has already marked it up. So it's kind of a question of, like, how much you want to try to engineer out of the algorithm, or not worry about that, but recognize it's there and try to have safeguards around it. And I think that kind of safeguards approach is maybe the most practical.
Probably also depends on the situation and how easy or hard it is to define what the actual, like how do you define the
The confounding
correlation
factor.
and what it is, I guess.
Yeah, absolutely.